This is FE Peer Review. The date is January the 12th, 2025. Designing a long-distance observation. Atmospheric refraction and why Sky-Free has the wrong approach. In this video, I want to touch on a point about designing a long-distance observation that I think would be helpful for people who are looking at doing these observations or looking at them. It has to do with how you deal with atmospheric refraction. I Can Science That just put out a video in which he's looking at one of these observations. It's an excellent video. I've provided a link in the description. I encourage people to go watch it. Somebody sent him the link to someone else's video, and he's analyzing the observation they've made. It's from a place in New Zealand, looking from a beach across the water to an island beyond. And he's trying to determine whether or not the water is concealing the shoreline of the beach of the island beyond. There was a comment, though, that somebody put in here that I wanted to address, and it's these folks called Sky-Free. It's a channel called Sky-Free. I've been aware of this channel for several years, and we'll take a brief look at their channel in a minute. But I'm just going to say, if you want to read their comment, pause the video and read the entire comment yourself. I'm not going to read the whole thing, but I am going to read a couple of points. So they said, great analysis. They always try to sound very friendly and positive in their channel. I appreciate your approach to this topic. Again, same thing. It would be great to have some temperature data to go off of as well. That's the only way to get an idea of what is happening with the light from distant objects traveling to the observer. It would be helpful to know the temperature of the nearby and distant water along the viewing route, the temperature of the air layers along the viewing route, etc. There's so much to consider with observations like these. Now, on the surface, that all sounds just fine, but there's a problem, a real problem in there, and it's just in one word, the word only. What they've done here is they've created a setup. They've said, for this observation to be useful, we need all of this data that we don't have, that's rather difficult to collect when somebody just wanders down to the beach with their camera. And since that data is not presented, and the only way to get an idea of what is happening is to have that data, we can now proceed to ignore the entire video and all the information presented. That's really what they're doing here. They're trying to set up a situation where they can reject valid, useful observations, data, and evidence that they don't like by defining a parameter on their own that they determine is vital, necessary, prerequisite, and without that, everything else is useless. So that's what they've done there in that first paragraph, and that is typical of the way they work. So if you come across Sky-Free or other people mouthing that kind of talk, challenge them. You say, Sky-Free, you say that's the only way to get an idea of what is happening. Why is that the only way? Show me the evidence that all of that other data you're saying is so vitally necessary is vitally necessary. I don't know that it necessarily is required that we have temperature gradients measured at every point across the water from our observer point to the island beyond. I don't know that that's strictly necessary. Tell me why you think it is. What evidence have you got for that? They go on. Both the vertical and horizontal temperature data along the viewing route are necessary to know. And then they give an example. The air above the island is going to have a different temperature gradient than the air above the water. True. That's true. But does it really matter that much? How much does it matter? Is it absolutely necessary, as they want to insist? The light traveling from the island may initially refract up and away from the warm surface, causing the island to appear lower than it actually is. Meanwhile, the light traveling to the observer from the nearby water may be refracting slightly down, raising the apparent position of the water. So what they're trying to do is they're trying to set up a situation. They're trying to suggest that it's possible that we have two different refraction effects happening at the same time, that we've got sinking out in the distance where the island is, pushing the apparent location of the island down, and we have looming in between the island and us, which appears to raise the surface of the water. This way, they can claim that it's actually a flat surface, and that the curvature that we're seeing is an effect of these two different raising and lowering, looming and sinking effects happening at the same time. That's the scenario they're trying to paint in order to cast doubt on the conclusion, the very clear conclusion that Iconscience drew, that there was a considerable portion of the island hidden by water's surface. So that's what they're doing. I think it's very underhanded, manipulative approach to using good science. Is it physically possible for us to have the island apparently sinking while the water in between is apparently looming? I don't know, maybe, but I think the conditions for that are going to be quite extraordinary, and I think they need to show that this is something routine and that shows up in almost every long distance observation over water like this one, because that's what it does. It shows up everywhere. We always see the same thing. Given that the island is far enough away, or that the ship is far enough away, or that the lighthouse is far enough away, we will see that the lower portion is concealed, and in a clear geometric relationship between the observer's location in terms of distance and elevation to the water and the observed object. We see that consistently, and they're trying to make as if it's a refraction effect. I'm going to slip in a little edit here and just point out that although it may be possible to make a case that the land mass of an island has enough of an influence on the atmospheric gradient as to cause something of an effect that Sky-Free is describing, that is certainly not the case with other objects that we see disappearing below the horizon at a distance. These tankers, for example, and container ships that we see dropping below the horizon, they do not have enough mass to influence the atmospheric gradient. They are moving within the same gradient as the water surfaces around them, and that also applies to things like wind turbines that we see disappearing below the horizon. Sky-Free is going to have to come up with a completely different fabricated artificial excuse to justify what we see in these images here. It will be interesting to see if they address that at some point. All right, I addressed them with a long response, and I'm going to read a few bits of it. I want to say, as far as the light traveling from the island may initially refract up, while light from the water may refract down, I responded to that with yes, although it's worth pointing out that the light traveling from the island also travels through the same atmosphere above the water that the light from the water passes through, and for a much longer distance than it traveled over the island. That's why I'm not convinced that what they even described is physically possible. They certainly need to show that it is. For reversed refraction, it's necessary to have a complete temperature inversion. Now, I'm not 100% sure that it's absolutely necessary, but I think that reversed refraction is almost always associated with the temperature inversion. This does occur, but the conditions for it tend to be unstable and it does not last long. It would not be the likely cause of an observed phenomenon if that same phenomenon were observed repeatedly over time. Where you are most likely to see it is in the boundary layer just above the water, a layer a few meters thick. Combined with high humidity, it might account, in this video, for the small bit of mirage we see along the horizon. Inversions are easy to identify because they give rise to the visible shimmering, quote, heat waves. So if they're interfering with an otherwise good observation, that observation can be tossed out and repeated when conditions are better for data collection. Inversions are most commonly seen at sea in warm weather, where the cold water cools the air just above the water's surface, while the air further up has been warmed by the sun. And then I gave them a reference that I think is useful. It's a book by a fellow named Humphreys, and it was page 449. I've got it here on archive.org. I'll put the link in the description as well. And it's this little bit on the right-hand side here on the right page, sinking. Instead of increasing the curvature of rays, the temperature distribution may be such as, on the contrary, to decrease it, and thereby cause objects normally on the horizon to sink quite beyond it. Such phenomena, exactly the reverse of looming, are also most frequently observed at sea. All right, so I'm going to take a brief look here at Skyfree's channel. You can see their channel here. What they do themselves, well, they look at other people's videos, but they do a lot of videos of their own where they put model boats on a lake, a small lake, for example, and then they get their camera and put their camera right down at the water level and follow. There's one. Refracted light and the illusion of curvature. So they've got a little model boat that they've put on the water surface, and they're photographing it with their camera right down at the surface of the water. That's typical of, they've done many of these. They've got yachts sailing in and out of a mirage with the underlying suggestion that this accounts for what we see in terms of boats going over the horizon and disappearing bottom up. They are trying to draw a parallel with their work using models and placing the camera right at the water level with these other observations we see of objects that disappear from bottom up. They don't talk a lot about flat Earth, but they're clearly aligned with flat Earth. If you read the comments on their videos, you see that what they're trying to do is basically give flat earthers a veneer of objective sounding, scientific sounding material to work with to combat all these long distance observations that do so much to damage flat Earth. That's Skyfree. All right, I want to get into one last thing here, and that has to do with how to set up or design a good observation. You know, design of experiments is a kind of a skill in its own way, and there are people that even specialize in helping scientists design their experiments so that they get the information they need and weed out and avoid confounding factors that might otherwise obscure the data they're trying to get. So after I had mentioned to them, you know, reverse refraction and visible heat waves from the shimmering heat waves and so forth, I said all these confounding effects that make it difficult to determine physical geometric relationships between the objects in the image based on the image itself are increased the closer the observer is to the water surface. The closer you put your camera down to the water, the more you're going to be messing up your imagery with atmospheric refraction. If your goal is to study atmospheric refraction, well, hey, that's great, fine. On the other hand, if your goal is to try to take images and extract from them geometric data about the actual locations of objects on the world here, where I'm on a beach, I'm looking 17 kilometers across the water to an object out there, and I want to get geometric relationships between that object and myself. I'd like to get rid of, as much as possible, anything that distorts that imagery. I need to design my observation to weed out and extract away distorting effects due to atmospheric refraction, if my goal is geometry. So, stand on the beach with a camera just above the water, and these atmospheric effects will dominate the image. Stand 2 to 3 meters above the beach, and the worst mess can be avoided. At Fort Takapuna, the observer location is about 10 to 12 meters above the waterline. That's a significant improvement. The best thing would be to find an observer location such as a beach with a nearby cliff 50 to 100 meters higher. Then, observations could be made at various elevations from the beach up to the cliff above. This would be helpful in 2 ways. It would help in identifying the data noise due to refraction effects, and it would provide valuable geometric data showing what happens with a change in elevation. Let's take a little dive into Google Earth here and see what could be done with this observation to improve it in terms of its design. Little Barrier Island is the island that we see off in the distance beyond the horizon in IconScienceThat's video. And the observer location was down here at a spot called Fort Takapuna. And it's right where I've got that little yellow line going. It was right in here. So for a start, we've got the question of the elevation of the observer. Now, a person could go right down to the water level if they wanted to and get some views from down there, and I would recommend that. We're going to start by assuming they've chosen a day with good weather that's going to tend to reduce refraction effects anyway. Go down to the water, put your camera pretty near down by the ground. I wouldn't go right down to the sand, but like a foot or two off the ground, 30 to 60 centimeters off the ground, and take a view. Take some good shots towards the Little Barrier Island. And then come up here, which is where they actually did their observation. And at this point, we're about 6 or 8, maybe 10 meters above the water line. Now set your camera up on a tripod, get it all nice and steady, get another few shots from, say, 10 meters above the water line. Now that's what they actually did, was that spot. Now by doing 2 sets of images, we've got more data to work with. It gives us valuable geometric information. But that's not the end of it. There's more that could be done here. 1.7 kilometers away, so not very far. What's that? A little less than a mile away. 1 mile away. There's a spot called the Summit here. This area here, I believe, is open to the public, and it would be possible to go up here to the top, and one would be at 60 meters above the water, 61 meters above mean sea level. So put your camera on a tripod, go out there during low tide, and you might get yourself maybe 63, 64 meters of elevation, and do another set of views. So there you go. That would be a really valuable addition to the data set, to have some views from this spot as well. Incidentally, we would be looking out to one thing I haven't checked is whether the Barrier Island is blocked from that location. Let's check. Let's see. Here's the Barrier Island. And we would be down in here, Fort Tuckanuck. All right, we might possibly run into an issue here as far as the observation. I wouldn't be able to know that without actually going there. But I think you get my point. Look for a good spot nearby that is yet higher than the one we were looking at before. Here's another elevated spot. I wonder if this is a place we could go. That's 81 meters. That's even better. Takarunga, Mount Victoria. If that's accessible to the public, that would be another place from which to do an observation. And that's also pretty near the original location, 1.5 kilometers away, even better. So there you go. That's what I would do if I was in the neighborhood. And I have half a notion to get out to New Zealand in the next year or two as far as a winter holiday, a break from the cold, damp Brittany weather that I live with most of the time. So if I do make it to New Zealand, I'll make sure to do a companion video to this one, but don't expect it anytime soon. I guess that gets at the root of what this video is about, which is designing a good observation for a long-distance view like this. I strongly recommend not going the route of Sky-Free. They intentionally introduce as much atmospheric disturbance into their observations as they can in order to, what can I say, obscure and make it more difficult to sort out whether we're seeing globe geometry or flat geometry. It is, in a sense, trying to use scientific techniques to hide the truth. I hesitate to use that phrase, but maybe I should say to obscure reality. We're trying to understand reality. And what Sky-Free is doing is trying to obscure that as much as possible and make it harder to determine whether what we're seeing tells us that we're living on a flat plane or a sphere. So there you go. That's my critique of Sky Free and my suggestion for ways to improve long-distance observations. All right, I guess I'm going to go through a bit more of Sky Free's comment here. I think it's worth going ahead and just covering it all. Sky Free actually writes in their comment, I think it's revealing, that showing it kind of sheds a light on what they're trying to achieve here. Assuming a planar Earth from an observer height of around 50 feet, viewing across 45 miles at an island with the highest point being about 2370 feet, that would put the top angle of the island at 0.55 degrees. The island appears somewhere around 0.25 degrees, close to the prediction for the globe Earth. However, over a distance of 45 miles, I believe it is very possible for a 30-degree displacement of the island downward due to upward sinking refraction across a planar Earth. We've observed objects around 0.2 degrees above the water surface appearing displaced downward, etc., even when the temperature variation of the air layers, etc., they're going on. So what they're saying here is that they have observed, documented on their channel, that these observations that apparently only work on a curved surface actually could work on a flat surface as well if we assume the kinds of refraction effects they're hypothesizing. So what they're trying to do is say you can't make a determination one way or the other. That's their goal here, to make all of these long-distance observation videos useless and moot and not a part of it and no longer a threat to flat Earth. They're trying to do it in such a way that it sounds all very scientific, but they have not actually shown that any of these refraction effects they're talking about are actually occurring and strong enough to actually do what they claim they do. What they have shown us is miniaturization, where they've taken small model boats and put them on a small pond and then set their camera literally inches, a few inches at most above the water level, and then done imagery like this where we see the extreme atmospheric disturbance occurring in those inches above the water level. And they've tried to make as if that observation they're doing here is in some way useful when we're looking at an island across a distance measured in many kilometers. So they're trying to use this kind of miniaturization approach to suggest that these effects we're seeing in this video here apply at the global scale. But they don't. Miniaturization isn't going to work for us here. Or I should say miniaturization isn't going to work for them, because those inches above the water surface, things are changing really fast. So you're getting these extreme distortions. But all you have to do is stand up 6 feet above the water and all of that disappears. You're not dealing with those layers of air that are just inches above the water surface. Now you're dealing with air that's 6 feet above the water surface. A whole different set of conditions. So you can't miniaturize these long-distance observations and expect to get something representative of the original full-scale observations. Anyhow, I think that does give us an insight into what their goal is here. It's to confound, it's to obscure, it's not to illuminate and help us understand reality better. Okay, I'm going to read a little bit more here, and then we'll do one last thing with Walter Bislin. Free Sky, I've been familiar with your channel for a couple of years. Actually, it's been more than that, probably 3 or 4. Something I noticed right away was that you made a conscious effort to conduct your observations in the zone that would maximize the distorting effects of atmospheric disturbance. Instead of designing your observations to try to cancel out refraction effects as much as possible, you do the opposite. You design them to maximize refraction effects. The result may yield interesting data about refraction, but it negates the value of the geometric data one might wish to gain through such an observation. So I'm pointing out that they are actually designing their observations to confound the data gathering regarding geometry. Typically, when people do these long-distance observations, their goal is to determine the geometric relationship between the observer, the target object, and the Earth's surface in between. As Icahn Science shows here, the goal was to determine whether the water surface was obstructing the view of the lower part of the island. These are geometric relationships. In this case, we want to avoid distortion effects of atmospheric refraction as much as possible. So the observation should be designed to achieve that. And I'm going to reiterate, they designed their observations to do the opposite. Your observations designed to maximize atmospheric refraction effects are interesting but not useful when it comes to a well-designed long-distance observation intended to clarify geometric relationships. The design of the latter should be such as to avoid atmospheric distortion effects as much as possible. That means choosing the right location and the best weather conditions. Ideally, it would be done at several elevations, but also on several different days, again, to identify and weed out any atmospheric effects. And then I basically tell them what I just showed you with Google Earth. Let's do one last thing here, and let's take a quick look into Walter Bislin's Advanced Earth Curve Calculator. Now this here is the page where he just derives all of the equations and shows all of the math behind the calculator tool. All of the math related to the refraction index and so forth. It's very valuable to read, even if you're not, even if you find that the math itself might be a little difficult. No need to actually go through the details of the equations. You can still learn a lot from reading his commentary about what he's doing along the way. So I recommend that, and I'll make sure to include a link to this in the description as well. So I wanted to mention this because Bislin's calculator is not just something that came from his imagination. It's not just something that he made up on his own. It has its roots in real science that long predates his own work. Let me get the page here. So here's the calculator, and like I said, this is based on long-standing science. This is not the invention of Walter Bislin. The calculator is great, but the math behind it is not his. It goes back a long way. I mentioned earlier this book by Humphreys called The Physics of the Air, and it was first published in 1920. This edition dates from the 1960s or something. But it's the book, it's one of the seminal books on the subject of atmospheric refraction. There's a lot of valuable information in it, and other atmospheric subjects as well. It covers a lot of material. But we looked at a page in it earlier about sinking and looming. So I wanted to mention this book just because I don't know if Bislin referred specifically to this book when he made his calculator, but it dates from, like I said, 1920. It's science that's been worked on by a lot of people for a long time. Okay, let's go back to the calculator now. Okay, I've put in here the observer height of 10 meters, target distance 72 kilometers, and target size of 722 meters. On the screen, I've got it split so that we've got flat Earth on one side and globe Earth on the other. I'm going to go to standard. I'm going to go to zero refraction. So this is just pure geometry here. That red and yellow is the target object that represents the island, and it's divided kind of ladder-like into 10 pieces. If you look at the one on the left, which is flat Earth, we see the entire island. Nothing is obscured of the base of the island. And we see 10 squares, starting with the yellow and going up. That gives us a convenient visual scale. Looking at the right half, we see globe, and we see that everything is lower. The eye level is above the horizon line, and we only see 1, 2, 3, 4, 5, 6 of the 10 squares of the island. So about 40% of the island is obscured below the waterline, the horizon. He gives us distance to the island, horizontal dip angle. So the angle that we're looking down to see the horizon is 0.1 degrees, whereas on the flat Earth side, the horizon would be at our eye level there, according to Bislin's model. And there's one limitation within this model that I'm going to bring up because it is relevant to what Sky Free was talking about. So this is zero refraction. If we go to standard refraction, we see that we now get an additional about 10% of the island visible. Originally, at zero refraction, we had 296.5 meters hidden. When we go to standard, we get 237 hidden. So we've gained some 58 meters of island looming or rising up because of refraction on the globe. With flat Earth, we get no change. The whole thing rises up, but we get no change with, we're not seeing any more or less of the island. We see the entire island the whole time. So this is where there's a limitation built into Bisland's calculator that doesn't cover the situation described by Sky-Free. Bisland's calculator, basically the atmospheric gradient in the far distance at the island is the same as the gradient in the mid distance, which would be the water, and the same at our observer location. It's the same atmospheric gradient throughout. And that's pretty typically, representative of the atmosphere over a distance of a few miles or a few kilometers. Now, what Sky-Free is proposing is that we are seeing a very different gradient at the island, such that it actually results in sinking, whereas the atmospheric gradient in the middle ground, where the water is, results in looming. So they're proposing a situation where the gradient is dramatically changing from the far distance to the middle distance. And that's not a situation that's included in Bisland's model. So there's no way to use Bisland's calculator to show that particular effect. There's a good reason why there's no way. It's because it's something that is very unlikely to occur, that the differences should be so extreme over a relatively short distance is not a common situation. So I invite Sky-Free to create a calculator of their own using standard atmospheric science, as Walter Bisland did in his reference page here, that has a component which allows us to set one atmospheric gradient in the distance and another in the middle ground. That way they could actually model, Sky-Free, they could actually model what they're describing in their comment. I don't have the math skills to do that, and so I can't make the model myself and test it against their comment, unfortunately. But since they're the ones that came up with the idea, I think it is appropriate to ask them to make such a model that we could all examine. And maybe people that are smarter than me, like Walter Bisland, could give it a look over as well. Again, Sky-Free may not feel they have the math or programming abilities to make such a model. I understand that. In that case, they need to get somebody with those abilities to work with them and help them create the model. Otherwise, it's just a lot of words in a comment on a YouTube video, and we're no farther along than we were before. I'll say one more thing here. I was looking at this final image from IconScience, and what we see, he overlaid Peak Finder imagery on the island and determined that the base of the island at the shoreline was approximately down here where I've got the mouse. And I wanted to point out that that's approximately a 40-60 distribution of 40% of the island hidden, 60 exposed, which does align nicely with what we saw on Bisland's calculator here with standard refraction. If anything, the refraction on that day of that observation may have been slightly higher because we did see a bit of mirage happening at the horizon line. So it might be that the refraction was a bit higher than standard on that day. That's not unusual when you're looking over at water surfaces. Anyhow, I think this is a good place to stop. I don't want this video to get too long. It's already long enough. Sky-Free, I just kind of wanted to point out that there's some things in their comment there that aren't obvious at first reading that I think people need to pay attention to. That's been my experience with them. I ended with, if I were in New Zealand, for example, I would return to Fort Takapuna, do an observation from the beach, say 2 meters above the water, another from the lawn above at 10 to 12 meters above the water. And then I'd go to that promontory or that other place I found that's about a kilometer and a half away, and it gets up to 80 meters high. This would be the perfect spot to set up a higher elevation observation. Done like that, this group of observations would yield valuable geometric data and almost entirely eliminate the kind of atmospheric distortion effects that you, Sky Free, are so concerned about within your own work. I have a hankering to visit New Zealand. I've never been there, and I hope in the next couple of years to make it out there during one of our winter breaks here. Okay, that's all. Enough. I wish you all a wonderful day. I hope you found this video useful and interesting. Something to keep in your back pocket the next time you're talking about atmospheric refraction and long-distance observations. If you did like it, give it a thumbs up, leave a comment. If you haven't already subscribed, please do so. Thank you. Bye-bye.